Ciao, welcome. I'm Giovanni Prodi, and I will provide an introduction to Experimental Gravitation and Cosmology study plan for the Master of Science in Physics at Trento. Bill Weber and Antonio Pereca will give more information after me, and you can find our contacts on the right of the slide. But you are free to think our younger colleagues that are addressing this kind of research with us. Yeah, let's go to the recommended courses for our study plan. Well, in addition to the mandatory courses, we have a recommendation for the elective core courses to take the experimental physics laboratory course, then to choose one among the quantum field theory 1, statistical mechanics, or computational physics, and then 3 among astroparticle physics, fundamental interactions, nuclear and subnuclear physics, condensed matter theory, atomic physics, physics of disordered systems, and solid-state physics 1. For the remaining courses, we want in particular to highlight the gravitational wave astronomy and multi-messenger observations, relativistic and multi-messenger astrophysics, general relativity and cosmology, and advanced interferometry that is planned to start in 2 years from now. In addition, you can consider seriously to take quantum optics, experimental techniques in nuclear and subnuclear physics, and, for instance, one additional laboratory course between Laboratory of Advanced Electronics and Laboratory of Advanced Photonics. But let me give you some motivation to choose the experimental physics and cosmology study plan. Well, underlying motivation is that gravity forges space-time. And of course, free-falling test masses, do follow curved trajectories and that see each other accelerating in a gravitational field. This slide shows the electromagnetic observation of the galactic center. And these observations provide compelling evidence for the existence, for instance, of a supermassive compact object, which is dark to electromagnetic at the center of our galaxy. In fact, it should be a supermassive black hole. Well, gravity has also waves, which are waves of curvature due to acceleration of matter energy. In the left, you can see a dance of galaxies. In the right, you can see the tidal deformation that gravitational waves produce on extended bodies. For instance, they can be detectable from relative acceleration of free-falling test masses. So gravitational waves are essential messengers to explore our universe because the universe is dark to electromagnetic mostly. Less than 5% of the universe is coupled to light, and less than 0.5% is bright in the electromagnetic messenger. Instead, gravity is sourced from all mass energy components. So gravitational waves probe the dynamics of all mass energy components. For instance, they have only predicted emission from the horizon of a black hole, and they can cross undisturbed any matter. For instance, they are traveling the universe from Big Bang to us. So depending on the frequency range that we can access, gravitational waves bring different information. Our group is actively involved in the research for the spaceborne interferometers LISA and for the terrestrial interferometers. The spaceborne interferometers look to sub-Earth band, which should be dominated by signals from binary supermassive black holes in the galactic nuclei, and also by signals coming from galactic stars, binaries of galactic stars. Instead, in the audio frequency of the terrestrial interferometers, the most prominent signals detected has been stellar mass black hole collisions, and we are aiming to probe physics of neutron stars and supernovae. Well, there are many more questions of fundamental physics, cosmology, nuclear physics, and astrophysics that could be investigated in the future observation of gravitational waves, thanks to the future observation of gravitational waves. What about our detectors? Well, the terrestrial detectors are kilometer-scale interferometers, and the operating ones are LIGO, Virgo, Kager. LISA is a spaceborne and instead has a size of millions of kilometers. And both of these research activities are inside international endeavors. So students are stimulated and, of course, immersed in an international environment. In 2015, we had the first detection by terrestrial gravitational wave detectors. Some colliding black hole signal generated 500 million years ago, which produced 10 to the -19 meter oscillations in the interferometers at Earth. This was crowning half a century of developments of detectors and 1 century of theoretical progresses, and has been the starting point of gravitational wave astronomy. In more recent years, we delivered some catalogs of gravitational wave transients made of mergers of compact objects, and for instance, led to the discoveries of an unexpected population of black holes more massive than previously thought. The counts of these events is rapidly increasing in time as detectors are upgraded and as more observation time is performed. Our local group at Trento in particular contributed directly both to the first detection of gravitational waves and to the more recent detection of the first intermediate mass black hole. This is some monster of 150 solar masses, which formed and emitted gravitational waves 7 billion years ago, when the universe was about half its current age. But the future is even more promising than this, because in the future we will have more sensitive detectors and we will cover more frequency bandwidth. In particular, LISA in space will be able to survive all the supermassive black hole collision occurring in the entire universe, plus plenty of other sources. On the terrestrial side, a strong research and development plan is up for next generation ground-based detectors. What can you learn beyond science of the universe if you join this study plan? Well, mostly fine experimental physics, strategies of measurement and control to a limit posed by fundamental noises, state-of-the-art inertial sensors, state-of-the-art interferometric techniques and data analysis methods, and much more. More information follows from my colleagues Bill Weber and Tony Pereca.
So good afternoon, I'm Bill Weber, and I'll be presenting on behalf of my colleagues in the Laboratory of Experimental Gravitation, the research that we're doing for the LISA mission, which aims to create an orbiting gravitational wave observatory. So LISA, the Laser Interferometer Space Antenna, aims to observe gravitational waves in the 100 microhertz to 1 hertz band, so periods of hours to seconds. And this includes some of the most massive gravitational wave sources, such as the million solar mass black holes at the center of galaxies that have a physics which is completely inaccessible from the ground just because of the size and the low frequencies of these sources. So LISA is composed of 3 spacecraft orbiting in a roughly equilateral triangle configuration around the sun. We observe the gravitational waves in the tidal deformation on a constellation of free-falling test masses. So in LISA, our antenna is the set of free-falling test masses, and our receiver or our readout is laser interferometry. At low frequencies, below several millihertz, the sensitivity is limited by the stray accelerations. It's limited by what we call the antenna noise, so the stray accelerations in our geodesic reference test masses. And a large part of our research here in Trento is dedicated to realizing the hardware needed to obtain a constellation of free-falling test masses with high accuracy, which means several femtometers per second squared acceleration noise, and demonstrating that this is actually experimentally possible. So the relevant hardware in this consists of the test masses themselves, which are heavy cubes of gold platinum, about 46 millimeters on the side. They're surrounded by an electrode housing, which is a Faraday cage, electrostatic shield, but also a capacitive position sensor at the nanometer level, and an electrostatic force actuator at the nanonewton level. These are inside a vacuum enclosure. They have a launch lock mechanism to protect them during the launch vibrations, and there's a UV light system for photoelectric discharge. The most important thing about this system is the quality of the free fall itself, and that's the hardest thing to demonstrate on the ground. So Trento led an ESA mission to demonstrate this, where we had 2 free-falling test masses inside one spacecraft, 40 centimeters apart. And our job now is to transfer this. We demonstrated this is possible. And we're now trying to transfer this into a case into the LISA observatory, where the test masses are 2.5 million kilometers apart. So what limits the quality of free fall are a series of forces which are rather simple to explain, but rather difficult to calculate from first principles. And so you really need a measurement. And we've done this on the ground with torsion pendulums. I'll just show a few of the things that we are testing or have testing. So we measure the photoelectric discharge of the test mass. We've been testing electrostatic actuators, which are generating nanonewton forces, but have to be stable at the femtonewton level. We've detected stray electrostatic fields inside the nominally equipotential Faraday conducting shields. We've detected electrostatic dissipation in nominal vacuum gap capacitors, and we've detected also Brownian motion from molecular impacts. So as far as our summing up, our main research for LISA is that of probing the experimental limits for free-falling test masses in experimental gravitation, so gravitational waves, but also other fundamental tests of gravity in space. We're the PI group for the Italian contribution, which is this gravitational reference sensor, and we're working on trying to measure and analyze these different noise sources on the ground. Just to give some ideas of thesis possibilities, there's implementation of the gravitational reference sensor for LISA and all sorts of analyses associated with this. Laboratory tests of free fall, including small force measurements, but also development for future experiments, including interferometry, electronics, analyzing and understanding the LISA Pathfinder test that we did in orbit over the last few years. And finally, trying to prepare to calibrate and analyze and understand the noise when we're actually doing LISA, and to distinguish in general between gravitational physics or instrument noise. And so I'm happy to respond to more questions. We're all available for this, and we refer you to our website if you want to see some references of theses, but also other publications of the group. So thanks for your time.
One division of the experimental gravitational area is the area of the ground-based gravitational wave detectors. In Trento, we accepted the big challenge to improve the sensitivity of the current gravitational wave detectors, in particular the one called Virgo. We also are part of the design team of the next generation of gravitational wave detectors, the so-called Einstein telescope. The Einstein telescope will be built on the success of the current second generation of gravitational wave detectors, the advanced Virgo and advanced LIGO, whose breakthrough discoveries in the past 5 years opened a new era of gravitational wave astronomy. The Einstein telescope will achieve a greatly improved sensitivity by increasing the size of the interferometer from 3 kilometers arm length of the current Virgo to 10 kilometers. And also by implementing new technologies, for example, cryogenic systems to cool down the main optics up to 10-20 Kelvin, and quantum technologies to reduce fluctuations of the light. What matters most for gravitational wave detectors is their sensitivity. The more sensitive the detectors are, and the smaller the signal that can be detected, the smaller are the detectable signals, the longer the distance to which we can detect them, and thus here the universe. The group in Trento is part of the worldwide LIGO Virgo collaboration. It is in charge of developing new techniques aimed to sense and reduce the optical losses. Once these techniques will be proved for Virgo, they can be extended to Einstein telescope. In particular, in Trento, we work on a technique based on the fact that the laser light has a shape. We properly manipulate the shape of the light and extract information about the losses, the optical losses of the interferometer. From this reading, we go further and correct or loss. We reduce the losses by reshaping the light. So we work on the shape of the light. In Trento, additionally, there is an area dedicated to analyze data taken from gravitational wave detectors. The next observation run will be in 2 years, which will fit perfectly with the new students coming at the University of Trento. For us, for the gravitational wave area, I like to say that our future is to go far back in time, when the universe was at the beginning of its life.